So I was mentioning about the some of the improvements on these decision trees that uh, has taken place that have taken place after it's uh, after 90 late 90s. I mean early 90s. One of the concept has been introduced that is called oblique decision tree. Now, in this case, the idea here is that in the decision tree, you consider the attributes are either discrete or continuous. And we know that how to make a continuous variables in the continuous domain attributes to make it into a discrete levels, because finally you have finite options of branching for when you check an attribute. Now, when you are checking a continuous variable, you can mostly what you are doing here. I mean, that is what you do. That no, you are checking certain threshold, and whether it is greater or less, depending upon even the equality also may be considered also in some cases, but usually greater or less for continuous variable. And depending upon that, you have uh, two branches, or you may have also more than that. But let us consider this binary situation that no, you have given a threshold, and then you have the branching on two descendant nodes, and in this way the decision is being taken. That means the conditions are checked, and finally you go to a leaf node to get a classification or regression, whatever problem you are regressed value, whatever problem you are going to solve. Now, the oblique decision tree rather considers a combination of attributes. So here in the usual decision tree, at every node, you are checking the conditions with respect to only a single attribute. But in an oblique decision tree, it is the combination of attribute uh, that is what is considered. And as I mentioned, that our context here is the attributes which are having this kind of numeric values. Mostly, they define certain continuous, a domain of continuous, say real space, if I say. Now, here, the as I mentioned, it's not a single attribute, it's a multiple attributes. Actually, the idea is quite simple and quite interesting, that if I consider a multidimensional space and real valued space, and then you may consider a hyperplane. You can define a hyperplane in that space. And as you know that a hyperplane in the multidimensional space, it divides the space into two halves. Uh, if you put a point in that space into that hyperplane, hyperplane can be represented by an equation. I mean, we have already mentioned this earlier also, that a hyperplane is nothing but linear combination of those attribute variables plus a constant term equal to you can say 0. So that is the definition of a hyperplane. Um, and if you put a point in that, uh, if you evaluate the value on that hyperplane, I'm using that expression. So that is the expression. It's a linear combination of attributes plus a constant term. So that also you need to consider when you express an hyperplane. And then if I give you a value, so let me give you uh, example. Suppose I have three variable, and three variables means actually three-dimensional. As you know that I can write it as say w1 x1. So let me denote these variables by these subscripts x1, x2, x3 instead of x, y, z. So w2 x2 and say w3 x3. This is a linear combination of the attributes when you are considering they are all continuous valued attribute, as I mentioned, and there has to be there will be one constant term also, which may be 0 also in some cases, and that should be equal to say 0. That is the equation of a hyperplane. Now you consider only this part of the expression. You consider only this part of the expression, right? Now, if I take any point in that space, so what is the dimension of this space? What is the dimension? How many attributes are there? There are 3 attributes. It's a 3 dimension. So if you take any point in the space, suppose you take a point x, y, z, and this is a point. And if I put this point, if I evaluate this expression using this point, you will get 3 kinds of values. Either it will be a positive, or it will be 0, or it will be negative. So the points which are giving the value positive, they are lying in the positive half of the hyperplane. Sometimes we use the term left half, right half when no, there is some meaning, but actually positive and negative can be also considered, whether it the half which includes the 0 and origin and which it does not include. So it doesn't matter. So just it is uh, sufficient to understand that there would be 2 partitions in the space, and also there is of course this hyperplane where it will be giving 0. So actually there are 3, but if I assume that no, that is a kind of some trivial case. I mean, usually there are 2 halves. One is the positive half and it is the negative half. And you consider when the value is 0, either you can keep it in the positive half or negative half in your condition. Is it like greater than equals or less than equals? So that equality conditions also included when you are doing branching. So now you understand that now if I give you at every node, instead of checking on the single attribute value, the conditions would be that this expression, suppose if it is greater than 0, then you have a branching at some to some node, and if it is less than 0, else you have a branching greater than equals 0 or less than equals 0, whatever. So you have a branching to some node, and this is so this is the way the decision tree can be formed. This is the way the decision process can be taken, and we call it oblique decision tree because this hyperplane. So in the special case of usual decision tree, this is also a hyperplane, isn't it? That is, say, I have checked with, suppose with respect to the attribute x1, and I am checking with x1 say greater than equal to some value theta, which means I have the corresponding hyperplane. It's an axis parallel hyperplane. It's an axis parallel hyperplane whose, as you understand, whose normal should be along the direction of x1. That is the axis. That is a normal direction. And in this case, it is basically plane defined by, it's parallel to x2, x3, plane defined by x2, x3 principal plane. So this is the idea. So normal case, you have axis parallel hyperplanes in the usual decision tree, but in oblique decision tree, you can have hyperplanes in any direction. And since this direction is not always parallel, that means it is not also always orthogonal to a particular plane, principal plane, or parallel to any axis. Then we, that's why we name it as oblique decision tree. So this is the kind of improvisation on the structure. It gives a better power of expression, and it can reduce the size of the tree significantly. The problem is that, let me go back because I have to remove that thing. So the problem is that how to select this kind of oblique hyperplane, how to get a hyperplane. That is, of course, computationally challenging. And there are different methodologies. I will upload that paper. You may read it, and you can go through this. One of the methodology is something like called central axis projection. So idea here is that as you can see, that actually you are trying to separate out your input instances into 2 sets, and you are trying to find out a hyperplane which is in fact separating these 2 sets, something like that. So there are some intuitive way of separating out 2 sets and getting a hyperplane which will approximately separate these two sets. Maybe it may not completely separate out them, but if you get an hyperplane, you will always define a positive part and the negative part. So that's not an issue. So if I give you an hyperplane, you can always partition your input instances into two halves, whatever you have at that node, and then you can check the corresponding information gain, etc. So the same measure you can do. Now, to get a better strategy, to get a better guess, these are certain strategies that followed. So you try to have two disjoint sets, and which should have a good separability property. So sometimes we use clustering also. So those things I will discuss later on. So that would be clear to you. So then you can use some perceptron training, linear discriminant analysis. So these are all related with those concepts are not really explained now, but you keep it into mind. And when we will discuss these things, then you will see that those are actually applied also while forming a decision tree. The other interesting, powerful use of decision tree, and which has become now mostly used instead of a single decision tree, you use a set of decision tree, and then we call a set of independent decision tree. We call it decision forest, and these decision trees you are trying to form in an uncorrelated fashion. It's a kind of random. Randomly, you are selecting a subset of attributes. So even if you have a large dimensional space, you can always consider that certain subspace. So randomly selected a subset, and you form a number of decision trees. So there is a question like, suppose you have m attributes. So how many subspaces you can consider there?
2 to the power m.
2 to the power m, because you have, it's a power set of attributes. So if each member of the power set will give you a subspace. So it is 2 to the power m, and so the question, how many to use, because it's an exponential number. So there it is. These are the issues that, of course, you have to resolve. As you see that from the engineering perspective, you have to make it pragmatic. So you should not consider all possible subspaces. You should be considering those which have much higher importance, maybe some combinations, or it can be completely random. With certain probability, you select the value of a certain number of less than m, and then you select a subspace. So that is what usually done. And for each, you form a full tree. That means it's a consistent decision tree with respect to the training examples. Then you apply certain kind of aggregation policy. So given an instance, you find out each decision tree is giving certain levels, certain class levels. It's a classification tree, for example. And then there are various aggregation policy like voting or average posterior probability of a class, etc. So you can compute them, and you can apply them to take a decision on these things. So with this, these are the two improvements that can be made, and I will upload these two papers which introduce these two concepts, and it would be interesting for you also to go through them and get more details. So the summary of this particular topic, what we have covered, that as you see that decision trees, it allows concept learning with noisy data. Also, it learns a set of rules. And in fact, we also discussed a technique by which, is there any question? Okay. So we also discussed an algorithm by which you are considering that you can directly get a rule without going through the decision tree algorithm. That also we discussed in our class under this topic. And there are certain basic information measure and gain functions that has been used for best first search of space of decision trees. ID3 algorithm has been detailed out. We see that in this algorithm we have a search space. Actually, search space is incomplete. I mean, you have a complete hypothesis, but no, yeah, search space is complete. Sorry, search space is complete, but you are going through certain heuristics. So, and using that heuristics greedily, you are going for a single hypothesis from that space. So it's a preference of shorter trees and the assumptions. And there are issues like overfitting that needs to be considered. And also there are many variations and extensions possible of these decision trees that we discussed, particularly the later variations on this oblique decision tree, random forest. Those you may find interesting, and you can have further details from the reference books from the papers. With this, let me stop for this topic. We will start the new topic next. But if you have any questions, let me know. Okay, so let me consider the is it visible?
Yes, sir.
Yes, sir.
Yes, sir.
Fine. So we'll start this new topic, and we'll review some of the basics of probability theory. I understand most of you are all well aware of this particular theory. You have that background, but just to review, so that because most of our topics are related to this theory later on, as you can see. So these are the things we'll be considering. So just a quick definitions of probability, and you can see that some of the concepts which are just simply introduced here using certain examples. Like you can consider an experiment like you can toss a coin twice, and then the results, all the possible outcomes of that experiments, that form your sample space. So if this is an event that not event, so the sample space is that all possible outcomes of an experiment. So if you toss a coin twice, there would be 4 such possibilities, as you can see, and it is shown as a string of um, the outcomes of a toss. And H represents head, T represents tails, that you can clearly understand. So there are these 4 possibilities. And we define an event which is a subset of possible outcomes. That's the definition of an event. So any subset you take of S, so that is the event. So you understand that your number of events in this case would be the cardinality of the power set of S. Now, if I consider a very abstract definition of a probability, uh, it says something like it's a kind of a measure. So these are the examples of events. Like as I mentioned, it's a subset. So probability of a event A, which is a number assigned to an event, and there are 3 axioms that has to be true. That is assumed for a probability measure. It has to be positive, or it can be 0, of course. And then the probability of the whole space, whole outcome space, should be equal to 1. That is one thing. And for every sequence of disjoint events, you have the union of all those events. If you consider the probability of union of all those events, and then that should be equal to sum of the probabilities of the events. Here AIs are all disjoint, so non-overlapping, and you are considering the. So the components, if you consider a set, and then no, you consider you consider the corresponding events which are partitions, events which are partitioning that set. So the probability, sum total of probability of all those events should be equal to the probability of the whole set S, and if that is the only universe, that is the only sample space, then this probability should be equal to 1. But it could be the probability of that set. That is what. So the simple definition of the probability that we have and we understand in a more naive way, that it's basically a kind of the proportion of occurrence of certain event with respect to the total possible outcomes. So that is a total possible events that is possible. So this is the kind of frequentist statistics, that is proportion of the events outcomes, rather outcomes within A with the total possible outcomes. That is what we consider. So now let us consider another interesting concept which is called conditional probability. So it tries to relate two events A and B with respect to the we want to measure that what is the probability that A occurs if B occurs, right? That probability A happens if B occurs. So that is simple definition of conditional probability. That is the definition of conditional probability. So take an example. So we sometimes pronounce it as probability A given B. So the notation you have observed that corresponding bar has been used. So it is basically pronounced as probability of A given B. So take this particular example that you have an event A which is the outcome which considers an outcome only 2 heads in a sequence, whereas B there are 2 possibilities of outcomes. So any of them, if it occurs, then it is B, right? So you are doing only 2 tosses. So outcome could be head and then tail, or tail and then head, right? So this is the definition of the event B. So now the question is that what is the conditional probability of A given B? That means suppose B has occurred. That means, which means that any of these 2 outcomes, one of these 2 outcomes has occurred. Is it clear? So then what should be the occurrence of A? That means 2 heads. So I hope you have already found out. So can you tell me that what is this probability, conditional probability of A given B in this case?
Zero.
Yeah, please.
Zero.
Zero.
Somebody say zero. Yeah, that's right. Okay. So any confusion? Does anyone have any confusion?
No, sir.
So you understand that no, HH is not is included into the set B here, of course, in this context. So if B occurs, definitely HH was not included there. So it has not occurred. Now let us take another example. Suppose definition of A and B is in this manner. So A is once again head and then head, and B is there are 2 possibilities. If any of one of them has occurred, then B is also occurs. That is head and head or tail and head. So what is the probability of B given A?
1.
Right.
1.
So you see that this is quite simple, and this is how conditional probability should be considered. Now let us consider another concept which is called joint probability, And no, this notation we have used in this manner, probability AB, and it means that both the events A and B occurred. Both the events A and B occurred. So that is what is the joint probability of A and B. Now here, here is once again this this example. You should tell me what is the probability, what is the joint probability of A and B?
Sir, 0.
It should be 0, right? So in these two toys, in this event, when you have done twice, you have tossed twice, both A and B occurrence should be 0. Actually, one of the way that joint probability can be measured, and we will be discussing Bayes theorem later on also. Joint probability is a very simple way of you can compute in this fashion, that it is basically probability of any of this. If you take A, then what is the probability of B given A? You can consider that the occurrence of A and then occurrence of B given A, or occurrence of B and then occurrence of A given B. Both are similar. Like so, if I compute them separately also, you will get this, isn't it? So, what is the probability of A?
1.
1 by 4.
1 by 4, right? Is it clear? Somebody said 1. I hope you understand. Right. Each toss is independent. That we'll be considering here. And so 1 by 4, and then of course probability of B given A is 0, so it is 0. So same the thing. Suppose this is a condition. Once again, the other one. So A is HH and B is HH TH. So what is the joint probability of A and B?
1 by 4.
1 by 4.
1 by?
1 by 2, sir.
See, if probability of A occurs, what is the probability of B given A? That is equal to 1, and probability of A equal to 1 by 4. What is the probability of A? Probability of A is 1 by 4 into probability of B given A. What is the probability of B given A? That is equal to 1, right? Is it clear? Somebody said 1 by 2. Is it clear? Is it clear now?
Yes, sir.
Okay. So there is another concept that I just mentioned earlier also. We say the independent occurrence of an event with respect to the other. So we say two events A and B are independent in case that probability of A given B equals probability of A. So whatever if B occurs, then also the probability of A is not getting affected. So that is the way we are defining the independence. There are other mathematical way, and this is also true then. No? It is mutual. Independence is mutual. So if A and B are independent, then you also should consider B and A are independent, and you have this particular thing. And also this is also true then. Then the joint occurrence of A and B should be probability of A into probability of B. So you see that now there are interesting relationships in mathematical relationships between the different kinds of conditional probabilities and joint probabilities with respect to the probability of events. So this can be extended. A set of events AI is independent it is when you have to consider, of course, the whole thing in totality. Then the intersection of all these events, basically it's joint occurrences of all these events also, that should be the product of the probability. So the so that is what is a rule of independence. So let us consider an example. Suppose you have a drug test, and you can see that there are two things in the test. So you have tested over a population, and which consists of two different genders, woman and man, and the test is successful or failure in these two subsets in a different proportion, right? You can consider the probability with respect to the whole population itself, and then that means probability of success, probability of failure with respect to whole population. Or you can also consider conditional probability of success given woman, conditional probability of success given man. So all these things can be considered here. There are no events like A is a patient, is a woman in this case, and say B, say drug fails, right? So the question is that will event A be independent from event B? So let me know your verdict.
So not independent.
So how do you find it? Can you explain?
So because probability of B is not equals to probability of B given A.
Right. So what is the probability of B?
Probability of failure is half.
Probability of failure is half, because total success is 2000 and total failure is 2000. Exactly. And what is the probability of, you are saying B given A?
0.1.
1800 by
Sorry, 0.9.
0.9. Right. Is it understood by everyone? Okay. So let me proceed. So we are discussing independence, of course. So further something, some explanations. So like consider the experiment of tossing a coin. And this is one example that you take this to another two examples I'm giving you. Sorry. So can you answer me? Consider example 1, what is happening there with respect to that question, and consider example 2. So what are your verdicts?
Last one will not be independent, sir.
Both of them are independent, isn't it?
Yeah.
So the interesting thing you see, you should take this, consider these examples See the second example, though A and B, both of them are independent, are they? I'm sorry.
None of them are.
Both of them are,
Last
in fact, not
last
independent.
one is not
Say,
independent.
what is probability of B given A? You just tell me. What is probability B given A?
0.
B given A?
0.
0.
I'm talking about example 1.
Oh, example 1.
I'm sorry. So actually my
1.
1. That is 1. Okay. So probability of B given A is 1. And what is probability of B?
1/4.
So which means no, it is not independent. Right? Probability of B is not equal to probability of B given A. Okay. Similarly, you consider example 2. What is the probability of B given A? I think you have answered already. 0. Right? And what is the probability of B? That is also 1/4. Is it clear? So they are not independent. They are dependent. In fact, that is what we would notice that, for example, 2, that though the sets are disjoint, but still they are dependent. So disjoint doesn't mean they are independence, right? It doesn't mean. So actually, it means doesn't imply. If A is independent from B and B is independent from C, will A be independent from C? What do you think? Anyone?
May or may not be.
It's not
May
necessarily.
not.
It's not necessarily. It does not imply. Basically, okay. These are those computations.
They are pairly independent.
They are
Pairly
they are
independent.
mutually independent. A is independent from B means B is also independent, and but they are mutual, but they are not transitive. So this is something you can say. Fine. Now we have derived, we have defined conditional probability. We have considered also the joint probability, and you can see actually the expressions what I mentioned. That is by definitions also, and that is consistent with respect to these definitions. And this is a relationship, and this is what is actually Bayes relationship, Bayes rule. We'll discuss further. Now you consider here this particular drug test. We have already answered some of you. Same question: what is probability of B given A, and what is probability of A given B? Can you compute these things? These two things.
Sir, both point time.
Both are fine. It's interesting. But that doesn't mean that it will be always equal. No? So given A is independent from B, what is the relationship between probability of A given B and probability of A? That is another question.
Equal.
Very right. So the Bayes rule. This is the Bayes rule that probability of B given A is equal to probability of joint probability of A and B divided by probability of A. Also, you can expand the numerator as probability of A given B into probability of B divided by probability of A. And that form is more popular in the Bayes rule. And in fact, the denominator also can be further expanded if I consider all possible components. I mean, all the disjoint components, and I can express in that term. So we'll later on we can see all those things. So this is one particular. Once again, some examples related to for understanding Bayes rule. So there are two events, R and W. R is actually here, it means rain, and W is the wet. So what is the probability? The grass is wet, W is grass is wet, and R is the event, it rains. So what is the probability that the grass is wet given rains? That table is given here. As you can see that if it rains, then the grass becomes wet. The probability is 0.7, and it remains dry is 0.3. Okay. Whereas if it does not rain, then the probability of it becomes so it remains wet is 0.4, maybe from some other water sources or some other things events, and it remains dry is 0.6. So you can see also that given the condition rain, there are only two outcomes of W. Either W happens or does not happen. So the given rain. So if I sum those probabilities, then that should be equal to 1. That is the interesting thing. And given not rain also, if you sum those two outcomes of W, that should be equal to 1. Similarly, but it is not the fact that grass is wet, and no, there could be many other outcomes, but it says 0.7. Okay, probability of R. So it is basically given, it is reflecting the probability of W given R, that condition only. So when you are providing this information, probability of W given R, automatically it also gives me no, it's not automatic. So basically, then also that's independently you have to also give the probability of W not given R. So these are two separate columns, as you can see. But given that condition, the sum total of the outcomes, the probability of sum total, that should be equal to 1. So now the question is that suppose it's a rainy day, and suppose W is the grass is wet. So what is the probability the other way? So that is, what is the probability that it has rained given that grass is wet, or it is a rainy day given that grass is wet? So there you can apply this Bayes rule. Can you compute it?
Sir, 0.7 by 1.1.
Point
7 by 1.1. Something 0.63.
let us compute. Huh? So probability of R given W. So this I can write as, say I'm writing simple P here. Say probability of W given R, okay, and then probability of R, right, and then divided by probability of, what should be this? Probability of
W.
W, right? Now, probability of W given R is given here. This is the probability of W given R. So this is 0.7, right? So this is 0.7. And then you get also probability of R. That is also given. Is it clear? So this is 0.8. Okay. So now we have to find out what is the probability of W. So how do you find out probability of W? So what are the possibilities with respect to happening of W? That probability W happens when it rains,
When it rains,
and
it not rains.
also probability of W when it does not rain. Is it clear? So that is what is probability of W. These are the two possibilities in this particular case, that either it rains or it does not rain. Then what are the probabilities? And then you can add them. Is it clear? So what is probability of W given R? W and R? That is probability of R given probability of W given R. So which is this one? 0.56. This is nothing but 0.56 once again. Is there any problem? This is what is probability of W given W and R. Joint probability of W and R. Probability of W given R into probability of R. And what is the probability of W given W and not R? What is probability of W given not R? It's 0.4. So it should be 0.4 into what is probability of 0.2. Right, 0.2. Right. So which means if I add them, it is 0.56 and then it becomes 0.08. It is 0.64, isn't it? Which means it is 0.64. Is it clear? Okay. So what should be the value in this case? Numerator is 0.56 and denominator is, just check whether I made any computation error, 0.64. Okay, 7 by 8, something like that. So quite high probability of rain. Any confusion? Is it clear to all of you? So that is what I was mentioning when I was telling that how to compute the new denominator there of Bayes rule. That is actually, it is called marginal probability of A. And while computing marginal probability of A, you are basically considering all possible conditions on for which A occurs, and you have to consider these joint occurrences of with all possible conditions, and then you sum them. But with respect to these only two events, rain or not rain, this is the way you compute them. So in that case, today I think my time is over, so I need to stop.